So since we're dealing with a continuous body, we're now going to be turning our sum into an integral. So our integral is going to be the position of our centre of mass is going to be equal to the integral of r times our little dm centre of mass, all our mass elements, divided by the integral of all our little mass elements. Of course, these integrals are all going from 0 to L because that's the length of our ruler, and so our total mass is going to be from there. Now, when you look at this, you notice that the integral from 0 to L of all the little mass elements is just going to be the total mass of the ruler. So we'll call this m. So this is equal to the integral from 0 to L of r dm over m, where m is the mass of the ruler. The issue now is we need to find out is what is an expression for the mass of each of these little individual mass elements in terms of other values that we know. So the other values we know, for example, are the density of the ruler, rho, the length of the ruler, and the cross-sectional area of the ruler. So if you remember that mass is equal to density times volume, then what we can have a look at is we will end up with our dm is going to be equal to the density dv, in the case we have a ruler of uniform density. And our dv is going to be our cross-sectional area times our little length variable in the ruler. So that is going to be equal to rho times our cross-sectional area times our length element. So this means that having done this, our integral will become RCM is equal to 1 over m, because that's outside the interval, times the integral of r rho a. So in this case, we then need to look at what is this value r. And so if you have a look along here, we have a look at this here, so the distance from this location O to here, that is our length r, which we can see is equal to a segment along the ruler. So in this case, our r, and then we have this little distance dr here. So our dl in this case could be considered to be just a little extension of r. So this will become 1 over m with the integral of r rho a dr. If we look at this carefully, we also want to know that this is going to be a definite integral because it's over the length of the ruler. So it's from 0 to L. Now that we've got this, we know that rho is a constant if we've got constant density along the ruler, so the ruler is uniform. We've got the cross-section area will be a constant because it's a constant size of the ruler. So this is going to equal, as rho and a are constant, we can bring those outside the integral. So we're going to have rho a over m, the integral from 0 to L of r dr. Now you know this integral is a simple polynomial integral, which equals rho a over m times r squared over 2 between 0 and L. And when we evaluate this integral from 0 to L, we end up with RCM is equal to rho a L squared over 2m. Now if we're looking at the total mass of the ruler, we can see that the rho times the volume is equal to the total mass of the ruler. So rho a L is equal to the mass. This is going to come down to L over 2, which is the answer we would expect for a uniform rod. We would expect the centre of mass to be in the middle. So in summary, when you've got a continuous mass distribution, the formula is very similar to discrete mass distributions. We simply use integrals instead of the summations, and you get the formula is displayed on the board. Now you should know the formula used to calculate the centre of mass of continuous mass distributions.